Okay, so we're gonna move on to 5.3 here, where we're gonna talk about diagonalization. Diagonalization. Okay, so the definition of a diagonal matrix is a matrix with zeros everywhere except on the main diagonal. And a square matrix is called diagonalizable if A is similar to a diagonal matrix. Okay, so that is A is diagonalizable if A is P times the diagonal matrix times P inverse for some P and some D. Let's see what else is super important to be able to do the examples. Steps to diagonalize a matrix A. This is the key here. All right, so first find the eigenvalues of A. So we've had lots of practice with that so far. Then you have to find eigenvectors that are associated with the eigenvalues. You really only need one. You guys know how to find the whole eigenspace. You just pick one vector from the eigenspace. Then you construct P using the eigenvectors as columns. So the matrix P is just take the eigenvectors, throw them into a matrix as columns. And then D is a diagonal matrix where the diagonal matrix are the eigenvalues that correspond to the eigenvectors that you just put into P. And then you find P inverse using your favorite method of finding an inverse. Okay, so what's the point of this diagonalization? It makes a lot of computations that can be really big and tedious shorter. In the example that I'll have you do in the activities, one such computation that can be shorter is raising a matrix to a power. Is quick because raising a diagonal matrix to a power is really easy. You just raise the diagonal entries to that power. I'm going to have you do one where you have to do like a to the fourth, 2 different ways. It might seem like it's not easier to do this diagonalization method, but if you were writing a computer program where your matrix was like 50 by 50, the number of computations you have to do to multiply a 50 by 50 matrix times a 50 by 50 matrix is huge, right? There's like tons of multiplications when you multiply each row times each column. So this actually saves a lot of computing time, right? As the matrix gets bigger, it saves more and more computing time. So it really is a big time saver. Even when we do these tiny examples, it doesn't seem like that, but it is. Okay, so let's jump into our example here. So basically, diagonalization is a way of factoring a matrix. So writing it as the product of 3 different matrices where the middle one is a diagonal matrix. And this is one special factorization that makes computations easier. There are lots and lots of other techniques that you learn in higher level linear algebra courses where you do some kind of special factorization of a matrix to make things easier. This is just one example. So I've already diagonalized this matrix A, right? So I already diagonalized it. So that means this is P, this is D, and this is P inverse. So what are the eigenvalues of A? 6 and 3. Yeah, because the diagonal matrix is made up of the eigenvalues. So we're kind of doing this backwards, right? You might be asked to find the diagonalization, find those 3 matrices. I've given it to you, so you say, well, I know that if I was finding it, I would put the eigenvalues on the diagonal in the middle matrix. So my eigenvalues are lambda equals 3 and lambda equals 6, and 6 happens twice, so we call that multiplicity 2. Okay. Give a basis for each eigenspace. So if I wanted to describe the eigenspace, this could be a hard problem, but because I've already diagonalized it for you, I know that the eigenvectors associated with each of the eigenvalues live in P. I picked eigenvalues already. So my basis for lambda equals 3 eigenspace is the column corresponding to it's the first column because the 3 is in the first column of D. So you take the first column of P. So it's just the vector 1, -3, -1. And then my basis for lambda equals 6. I have 6 is in 2 columns, so you take the 2 vectors from those 2 corresponding columns in P. And I get 0, 1, 1, and 2, -1, 0. Okay, so evaluating a to the fourth 2 ways, I could do a times a times a times a. Or I could do p times d to the fourth times p inverse. So this is 4 multiplications. 4 multiplications of 3 by 3 matrices. But when I do it this way, I just have to do p times d to the fourth times p inverse. D to the fourth is really easy. You can do it in your head. So this brings it down to 3 multiplications of 3 by 3 matrices. So if A were really big, a really big matrix, or if I was raising to a much higher power, right, like a to the 18th, this would save you a ton of time if it was a to the 18th. I'm not going to do it all out, but that's the idea. Just saves you a lot of time.